This conference will now be recorded.
Yeah, myself, Shriram Kulkarni. I'm from Electronics and Communication Department. So today we'll be discussing on basic electronics. So first we'll start with syllabus. Yeah, the subject code is 18 ELN 14. So module 1 starts with semiconductor diodes. So PN junction diode and its characteristics. So basically your diode can be used to so diode can be used. Yeah. So PN junction diode. So
This conference will now be recorded.
yeah, myself, Shriram Kulkarni. I'm working as assistant professor in ENC department. Okay. So today I'll be discussing on basic electronics. Our subject code is 18 ELN 14. So model 1. So it's a semiconductor diodes and its applications. So it basically focus on PN junction diode, its characteristics, and application of diode as a half wave rectifier, full wave rectifier, and bridge rectifier. Then after that, Zener diode. Zener diode as a voltage regulator. Then numerical examples. Then photodiode, LED, and finally we are focusing on voltage regulator. In module 2, it covers BJT and its applications. So BJT, bipolar junction transistor, at a time either it can be used as amplifier or switch. Okay. Then feedback amplifiers, like why we require feedback amplifiers, its principal properties, and what about feedback, why we need negative feedback and all. Then oscillators. So then classification of oscillators, Barson criteria. Okay. Then RC phase shift oscillator, when bridge oscillator and all. Then module 3 will be focusing on FET, that is field effect transistors, FET construction, operation, drain characteristics, depletion and enhancement, metal oxide semiconductor MOSFET, and finally CMOS. Followed by silicon controlled rectifier, characteristics of SCR and all. Then fourth module is operational amplifier and its applications. Like it starts with introduction to op-amp, ideal op-amp, why we require operational amplifier, configuration, like how many pins it has got, right? Then op-amp applications like inverting amplifier, non-inverting amplifier, voltage follower, adder, subtractor, integrator, differentiator, comparator. Then designing of inverting, non-inverting amplifiers and some problems on the same. Then module 5 focuses on digital electronics fundamentals, like difference between analog and digital signals, like then number systems, how many number systems we have got, like binary number system, decimal number system, hexadecimal number system, octal number system, then conversion between these different types of numbers, followed by Boolean algebra, why we require Boolean algebra, then basic and universal gates, full adder, multiplexer, decoder, flip-flops and all. And finally, we are focusing on principle of operation of mobile phone. Now we'll check some basics of number systems. Yeah. number system, then representation of numbers with different radix, conversion of numbers from one radix to another radix, component of number, then binary arithmetic. Yeah. A system of for representing number of certain type. Like for example, there are several types for representing the counting numbers, right? So these include the usual base 10 or decimal. Okay. Yeah, we have some different types of numbers here. Say first column system, second column base, third one symbol, based by or used by humans or used in computers. See, I can divide numbers like decimal numbers, binary number, octal number, and hexadecimal number. Decimal number means the range lies between 0 to 9, and radix or base used for this is 10. Similarly, in case of binary number, the range would be from 0 to 1, right? And if you count from 0 to 1, the count will become 2. So we are taking radix as or base as 2. Similarly, in case of decimal number system, the range lies between 0 to 9. So if we count from 0 to 9, the count becomes 10. Then similarly, octal numbers. Octal numbers means the lies between the number, octal number range, it lies between 0 to 7. And if we count from 0 to 7, the count will become 8. So we are using the radix as 8 here. So next one is hexadecimal numbers. So hexadecimal number means the range lies between 0 to 15. So if we start counting from 0 to 15, we will end with count as 16. So we are using radix or base as 16 here. In we can take any example like decimal number. You can take any number, right? That will come under decimal number system, like 15, 195, 25.35. You can take any numbers. Okay, that number will lie between 0 to 9. Then binary number example, I can say like 101, 10.1011. Okay, so you can say for example 101. It has got 3 bits, 1, 0, and 1. So first number 1, that lies between 0 to 1. Second bit 0, that lies again between 0 to 1. Then final third bit 1, that also lies between 0 to 1. So I can call it as binary number. Similarly, octal number means, for example, 145. I can say 145 is an octal number. Bit 1 because that 1 lies between 0 to 7, 4 lies between 0 to 7, and again 5 lies between 0 to 7. Similarly, hexadecimal number system. So hexadecimal means the range will be from 0 to F. Means 0 to 9, it acts as decimal number, but 10 we are writing it as A in case of hexadecimal. Similarly, 11 by B, then F indicates 15. Okay. So can we use decimal number in day-to-day life? Yes, but binary, octal, and hexadecimal usually we won't use, right? And can we use these numbers in computers? Decimal number? No, we cannot use. Then binary we'll use. Then octal and hexa, okay, we won't use. Then counting, as I said, a decimal 0. Count. So decimal number first column, second column binary, third one octal, fourth one hexadecimal. Just I'm showing one conversion here. If it is decimal is 0 means in binary I need to write it as 0 only. In octal also it is 0. In hexadecimal it is 0 only. Say decimal number is 1. How I can express in binary? 1. See, binary means a single bit. It can take either 0 or 1. Okay. Next octal number 1, hexadecimal 1, then 2. See, this 2 is a decimal number. Why? Because this 2 lies between 0 to 9. So I can call it as decimal number. Then how I can express in binary? See, this binary I can write like weights, binary weights. See, this rightmost bits I can write 2 raised to 0. Then rightmost bit, this I am calling it as LSB, least significant bit, because it will carry the minimum value. Then next one, 1. See, if I add these two, I am getting answer as 2. See, because 2 raised to 0 into 0 is 0, 2 raised to 1 into 1 is 1. So 0 plus 2 is 2. In octal, I am writing it as 2. In hexadecimal also, I am writing it as 2. Similarly, if I take 15, last one, 15, I can write in binary as 1, 1, 1, 1. If I express in binary weights, the rightmost bit, I can show it as 2 raised to 0, 2 raised to 1, 2 square, 2 cube. So if I add all the weights multiplied by 1, 1, 1, 1, like 2 raised to 0 into 1 is 1, because anything raised to 0 is 1. Then 2 raised to 1 into 1, 2 raised to 2 into 1, 2 raised to 3 into 1. So if I add all 4, it will become 8 plus 4 plus 2 plus 1. So final answer will become 50. Okay. So in octal, we'll see in detail how exactly we can convert from decimal to octal and all. It will become 17. Right. Then in hexadecimal, I'm not supposed to write it as 15. Instead of 15, I'm writing it as F. Then different types of conversions. I can say there are many types of conversions. Like I can start with binary to decimal, binary to decimal, binary to octal, binary to hexadecimal. Then I can express this same in reverse way. Decimal to binary. Then yeah, we'll start like this. Binary to decimal, octal to decimal, hexadecimal to decimal. Then decimal to binary, decimal to octal, decimal to hexadecimal. Okay. Then again octal to hexadecimal, hexadecimal to octal. Okay. We can convert it in many ways. So first we'll check binary to octal conversion. So in case of binary to octal conversion, say let's start with one example, like 1010101. So we need to convert this binary to octal, right? So what we need to do is we need to make a group of 3 bits. We need to make a group of 3 bits and we need to move from right to left, okay? Right to left and make a group of 3 bits. Why only 3 bits? Because maximum bits required to express any octal number is 3. Okay? Means 7. To express 7, how many bits we require? 3 bits, 777. So these are the minimum bits, right? So we are making a group of 3 bits. Suppose if I am converting from binary to hexadecimal means, so the maximum number that we can use in hexadecimal is 15. To express that 15 in binary, again we require minimum 4 bits. Okay, 1111. So in case of binary to hexadecimal conversion, we need to make a group of 4 bits. As it is from binary to octal, so we need to make a group of 3 bits. Okay, and we need to move to the left. So this is one group, this is one group, and we have left with only a single bit. So to make a group, we need to add 2 zeros after 1. Okay, so this becomes 1, 2, 1, 2. So next is octal to binary. So if we are converting from octal to binary, what we need to do is we need to represent or we need to replace each octal bit with the with its binary equivalent. Binary equivalent means again we need to take 3 bits. So 2 means I can write 010, 5 means 101, 7 means 111. So if I combine all these bits, it will become 010, 101, 111. So this is the binary equivalent of 257. So what we did here in case of binary to octal conversion, we need to move from left to, so we need to move from right to left, and while moving we need to make a group of 3 bits. So if we are getting any shortage of bits means we need to add those many zeros to form a valid group here. Okay. So again in case of octal to binary, go on replacing each octal number by its 3-bit binary. Then binary to hexadecimal. So in case of binary to hexadecimal conversion, what we are doing is we are making a group of 4 bits. We are making a group of 4 bits, and we need to move from right to left. Means we need to move towards our left side. Okay. So we can take this example 1010111011. So I'll move towards left side. So this will become one group. So this is one group, and I'm getting only 2 bits. So to make it as a group, I need to add 2 more zeros. So after adding, if I want, I can show 2 zeros here. So this becomes 0010, 1011, 1011. So 2BB. I can read like 2BB. B means 1 plus 2 plus 8. 8 plus 2 plus 1. It's 11. B means 12 it is. Okay. Because in hexadecimal conversion, I'm not supposed to use 11 or 12. Right? Right. So 1011 means B. 1011 means B. Suppose if I get 1111 means instead of writing it as 15, I need to write it as F. So next one is hexadecimal to binary conversion. It is same like octal to binary conversion. But what we are doing is we need to replace each hexadecimal number by its 4-bit binary. So I can check here 25A0. It's a hexadecimal number, right? So go on replacing each hexadecimal number by its 4-bit binary equivalent. So 2 I can write it as 0010. 5 I can write 0101. A I can write it as 1010. Then 0 I can write it as 0000. Why again 4 bits we require? Because we need minimum 4 bits to represent the maximum hexadecimal value, it is 15. So while making groups also we are considering 4 bits, and while converting also we are considering 4 bits. Then octal to hexadecimal. Okay, so while converting from octal to hexadecimal, I can say there are many ways. So one way of converting octal to hexadecimal is, first method is I can convert octal to binary, then binary to hexadecimal. That is one way of conversion. Second way is octal to decimal, then decimal to hexadecimal. That is the second way of conversion. Okay. Again, hexadecimal to octal. Again, I can say there are 2 methods or 2 ways. One is hexadecimal to binary, right? Then binary to octal. First way. Second way, hexadecimal to decimal, then decimal to octal. So depending on our convenience, we can use the particular method. Right. So next comes binary to decimal conversion. So while converting from binary to decimal, what we are doing is we are expressing the given binary number with respect to some polynomial format. So I can show like this. For example, 1011.0 1 1. It has got 1 2 3 4 5 6 including this fractional point. So first I'll consider 1011. It's a whole part. Then 0.11 it's a fractional part. So what I'm doing is, see, I'll start with leftmost bit irrespective of this fractional point. I'll start with leftmost bit, and I'll try to cover only the whole number. Then I'll be covering the fractional part. So in the whole number, I got 4 bits, 1 0 1 1. So I'll write the first bit, that is leftmost bit, that is 1. After 1, I got 3 bits, 0 1 1. Right? So I'm writing it as 1 into 2 raised to 3 because I'm considering only whole number. And after this one, I got 3 bits. So 1 into 2 cube plus this 0 into 2 square, because after 0, I got 2 bits plus 1 into plus 1 into 2 raised to 1. Yeah, there it is. 1 into 1, this one into 2 raised to 1 plus 1 into 2 raised to 0. Now I need to check the fractional part. Plus 1 into 2 raised to minus 1 plus 1 into 2 raised to minus 2. So that becomes 8 plus 0 plus 2 plus 1 plus 0.5 plus 0.25. So that becomes 11.75. So can I call this as a decimal number? Yes, because it has got again 4 numbers or 4 bits, 1, 1, 7 and 5. I'll check the first number. 1, will it lie between 0 to 9? Because we are converting from binary to decimal. So 1 lies between 0 to 9. This 1 lies between 0 to 9. This 7 lies between 0 to 9. And this 5 lies between 0 to 9. So all these 4 bits, they lie between 0 to 9. So I can call it as the decimal number. Next is decimal to any case. Oh, sorry, decimal to any base. So it can be anything like a decimal to binary, decimal to octal, or decimal to hexadecimal. Right? Convert the integer part, successful division method. Second step, convert fractional part, successive multiplication method. See, what we are doing is basically, if it's a integer part or if it's a whole number, say for example, I'm converting from decimal to binary. Right? Decimal to binary means I need to divide the given decimal number, say for example 8. So I need to divide this whole number successively by 2 and keep the remainder part. Okay, and I need to take the bits from bottom to top. So that will be the converted answer. Right. Then in case of decimal to octal also, I can follow the same method. And again, in case of decimal to hex also, I can follow the same method. If it's a fractional part, means instead of division, I need to multiply by 2 successively and track the integer part. And I need to consider the bits from top to bottom. So that is the method. Right. So it can be anything like decimal to binary, decimal to octal, and decimal to hexadecimal. So whenever a decimal comes first, remember we need to divide. Then what format you are converting? If it is binary, means divide by 2. If it is octal, means divide by 8. If it is hexadecimal, means divide by 16. I can check with respect to an example here. Say 125. It's a decimal number. I need to convert this decimal into binary. So go on dividing this decimal number by successively by 2 and track the remainder part. So 125 by 2, I'm getting 62 and remainder is 1. Go on dividing. So 62 by 2, 31, remainder 0. Till here. I can stop at this point because I cannot divide further this 0 by 2. Right? So I can read the bits from bottom to top, like 0, 1, 1, 1, 1, 1, 0, 1. So this is my answer. So what I did here, if it is a whole or integer part, go on dividing by 2 successively, then track the remainder part. Read the bits from bottom to top. So that will become triple one. Sorry, how many ones are there? 1, 2, 3, 4, 5. 5 ones, 1, 2, 3, 4, 5, then 0, 0. See, why we have not considered this 0? See, before this one, you can add n number of zeros, but the final value will not change. So we have skipped this 0 here. So next is ones complement. So ones complement means what we are doing is, say we have one binary number, 101. What we are doing is we are complementing each bit. Say for example, means we are performing NOT operation or inversion operation. Say for example, we have 1 1 0 1 0 0 1 0. I want to find the ones complement of this given binary number. So what I need to do is I need to go on replacing 0 by 1 and 1 by 0. So that so 1 should be replaced by 0, 1 by 0, 0 by 1, 1 by 0, 0 by 1, 0 by 1, 1 by 0 and 0 by 1. So this is the ones complement of given number 1 1 0 1 0 0 1 0. Okay. Then what about two's complement? See, two's complement means, or I can say if we are checking two's complement of any given binary number means, directly you cannot calculate two's complement. So first thing is we need to calculate the ones complement of given binary number, and we need to add 1 to it at the LSB. For example, say I have this number 00100011. For this, I need to calculate the two's complement. So what we need to do? First step is before calculating two's complement, I need to calculate the ones complement of this given number. So it will become 1 1 0 1 1 1 0 0. Then add 1 to it at the LSB set. LSB means it will have the minimum value, and this is MSB. It will have the maximum weightage or value. So that will become, after addition, I'm getting it as 1 0 1 1 1 0 1 1. Okay. So this is two's complement of any given number. So what I did here, first before calculating two's complement, I need to calculate one's complement, right? Then after getting one's complement of any given number, I need to add 1 at the leftmost side. So that could become two's complement of the number. 9's complement and 10's complement, it is not there for the syllabus. Then binary addition. So binary addition means we are adding, we need two binary numbers. So for that we have got some rules here. Okay. The first one, if I add 0 with 0, I'm getting sum as 0 and carry as 0. If I'm adding 0 with 1 means I'm getting sum as 1, carry as 0. Third rule, if I'm adding 1 with 0 means again I'm getting sum as 1 and carry as 0. So if I add 1 with 1, I'm getting sum as 0, carry as 1. So these are the 4 rules. So these rules we need to remember if we are performing any binary addition operation. So for example, 1100 plus 0110. So we need to add these two binary numbers by considering these 4 binary rules. So how it will work? 0 plus 0, 0, 0 plus 1, 1. Sum I am writing here. Carry, if it is generated means I am writing at the next level. So 1 plus 1, sum is 0, carry is being generated here. So 1 plus 0 plus 1. So 1 plus 1, sum is 0, carry is generated as 1. So this one I'm writing as it is. So the answer becomes 1 0 0 1 0. So this is about binary addition. So next comes binary subtraction. So here also we are following 4 rules, that 0 minus 0 0, 0 minus 1 1, borrow as 1, 1 minus 0 as 1, 1 minus 1 is 0. Okay. So we'll check with respect to one example. Say we have two numbers 0 1 0 1 minus 0 1 1 0. See, while adding or while subtracting, make sure that you are performing from the or you are starting from LSB part. So 1 minus 0 is 1, 0 minus 1 is 1, borrow is being generated. So 1 minus 1 minus 1 is 1. Again, that 1 I'm keeping as it is. So 1, 1, 1, 1. So multiplication and division, it's not there for the syllabus. Okay. So, it's about number systems and number conversions. Right. Then again, once we complete this, means next we have got Boolean algebra. So Boolean algebra means it's a mathematical tool, so that can be used. So Boolean algebra means basically it's a mathematical tool that can be used to design or evaluate any of the digital system. So after that we have got so once we finish Boolean algebra, next comes combinational circuit and sequential circuits. So combinational circuit means it's a circuit where we can expect the output dependency only on the input. Means output is dependent only on the input. If that is the case, we can call it as combinational circuit. We have got some logic gates. What do you mean by logic gates? It's an electronic circuit, right? So that makes some decision. So for example, AND gate. AND gate means it's a logical multiplication, right? Again, we have got some different types: 2-input AND gate, 3-input AND gate. So 2-input AND gate means it can take only 2 inputs at a time and will produce a single output. So those 2 inputs, how we can give, it will be like 0, 0, 0, 1, 1, 0, and 1, 1. Right. So this is about 2-input AND gate and logical multiplication. So if I check the truth table, it will become it will be like I'm getting output as high if and only if both the inputs are high. In case of AND gate, it's a logical multiplication. Similarly, if I take OR gate means logical addition, NOT gate means logical complementing. Then you can take any logic gate that comes under combination circuit. Why? Because the output is dependent only on the input. So then we got some encoder circuits, decoder circuits, multiplexer, and all. So these will also come under the combinational circuit because output is mainly dependent on the input. So next comes sequential circuits. So sequential circuits means again these are electronic circuits where output is dependent on two things or two parameters. First parameter is input. Second parameter is previous output. Right? In case of combination circuit, the output was only dependent on input. But in sequential circuit, this will dependent on two things. One is previous input, present input, and previous output. For example, I can say flip-flops, counters, and all. What is flip-flop? Again, flip-flop is an electronic circuit that holds only one bit at a time, either 0 or 1. But the thing is, the output is again dependent on two parameters. Even I can consider clock pulse. Okay. Then after this, we have registers. Register is a combination of flip-flops again, right? Again, they're also the output dependent on two things or two parameters, right? So flip-flops, shift registers, counters, right? Counters means it's a circuit again that will count from starting number to the some predefined number. Say we have designed one counter that say it's counting from 0 to 9. So I can call it as a decade counter. Right? So it's about counter and all. Then next part will be on communication part. So communication means it can be from say one person to another person, or from one point to another point. So if a faculty is giving lecture in a classroom, means it will be like a communication only, right? And what about medium? I can say air is the medium, right? Then in communication, again we have got many things like modulation, demodulation, and basically modulation means it's a process where we can uh, increase the strength of the message signal or voice, so that it can travel for the longer distances without any disturbance. So that is modulation. That is the purpose of modulation. For that, we are considering carrier signal also. So carrier signal, what it does is it helps the message signal to travel for a longer distance without any interference or disturbance. So that is the purpose of using the carrier signal here. So if I consider the main components of the communication system is information source, transmitter, then followed by channel, then receiver, then destination. So at the transmitter side, we are performing modulation technique. So modulation technique is a technique where you can add carrier, or where you can mix carrier signal with the message signal. That mixture can be traveled for a longer distance, right? Then at the receiver side, the reverse operation we are performing, that is we are suppressing carrier, then taking out only the message signal. Then between transmitter and receiver, I can show one channel, can be anything, like a coaxial cable or even optical fiber, right? So channel can be used, right? So information source. Then if I can show one more input transducer here. So input transducer, what it does, it converts the original signal or original message that you are transmitting, that is being converted from main like message signal into electrical signal. So that electrical signal is given to the transmitter. Okay. Then modulation process takes place, followed by channel. Then after channel, again receiver. Receiver, what it does, it removes the carrier and retrieves back the modulating or message signal that is being again fed to the output transducer. So output transducer, what it does, it converts the electrical signal back to the message signal. So that is done by the output transducer. Then output transducer to the destination, means where exactly you want to transmit that particular message. That is about basic communication system. Okay.